In this video, we'll learn how to calculate work in the special case of one dimension with a constant force. Work itself is a scalar. It can be positive or negative, but it is the product of two vectors. In this case, where we only have motion in one dimension, and if the force is constant throughout, we have a very simple expression. The work is equal to the force times the displacement, where those two vectors, force and displacement, are represented in our 1D notation. To see how that works, imagine you're lifting up a bag of dog food 2 meters. The mass of the bag of dog food is 20 kilograms. If I were to do a free body diagram for the bag, I would say there's some sort of contact force, that's you lifting it up. There's also the force of gravity on the bag. I have to identify a positive direction, so I'll identify positive up. First, I want to calculate the work done by gravity on the bag. So I need to know the displacement. The displacement is a vector, and it's the vector final position minus the vector initial position. Also, in one dimension, it's handy just to be able to draw from the initial point to the final point, and that vector represents the vector of displacement. So in this case, our displacement is a vector. It has a length of 2 meters, and it is positive because I've identified the positive x to be up. And then in our notation, we just represent the vector as the magnitude where the sign indicates the direction. The force due to gravity has a magnitude of mg, and it's pointing in the negative x direction given our coordinate system. I've identified its simple notation there. The work due to gravity is just the product of these two. So here the work is negative 392 joules. What is the work done by the contact force on the bag? The contact force has some magnitude, and it's pointing in the positive x direction. And we really don't know what that is. So let's specify this a little further. If I'm lifting up this bag, I can think of there's this initial where I have a high force where I'm accelerating it. Let's say I lift over this 2 meters at a constant force where the object itself is going at a constant velocity, then it slows down at the end a little bit. So we just want to look in this middle region where we're saying the object is being lifted at a constant velocity. If that's true, then there's no acceleration, which means there's no net force, which tells us that the magnitude of this contact force is the same as the force due to gravity. And that's to help us simplify the problem because what we really want to know is what the work is. So if I write out that vector then in simplified form, I get that. And I can calculate the work, which is then that force times the displacement, or a positive 392 joules. Let's do another simple example where we come up with a net work. Here I have a mass of 2 kilograms that's being pushed along the ground. It's restricted to move in one dimension, so I have sort of my one-dimensional model where I can ignore any forces in the vertical dimension. So there's a pushing force on this block of 24 newtons. There's also a horizontal contact force due to friction of 16 newtons to the left. It moves the displacement under these conditions, everything's constant, in a straight line 4 meters to the right. So what are the work done by each force and the net work? First, I'm going to do a free body diagram. I have a pushing force to the right, a frictional force to the left, and I've identified positive x to the right. So I can go ahead and calculate the work due to the pushing force, which is that force in our one-dimensional notation, which is a positive 24 newtons, times the displacement in that same notation, which is a positive 4 meters, and I get 96 joules. The same thing with the frictional force. Since it's pointing in the negative x direction, I represent that as negative 16. The displacement is the same, it's still 4 meters to the right. The work done by the frictional force is negative 64 joules. So remember, a positive work is adding energy to the system, and the negative work is removing energy from the system. So that says the net work added to the system is just the sum of the individual works, which is 32 joules. There's another way to do this, which is to come up with the net force. The net force is the vector sum of this pushing force plus friction. So that's plus 24 plus a negative 16, which is 8 newtons. The total work then is just the work done by the net force. And in this case, that's a positive 8 times 4, or 32 joules, which conveniently checks out with the method we used before.